Oh, I'm sorry. And the other thing is, after the talk, there's going to be coffee and cookies up on the 5th floor in the lounge.
So Melanie suggested I give a Blackboard talk so that there could be lots of questions. I think that's a really good idea. But I could just stop here and take questions, and I'm sure we can fill the hour. But I hope this goes well. I haven't actually given this as a Blackboard talk before. And so I mean, actually yesterday in the colloquium, you saw sort of the basic argument. There's, you know, it's simple enough. This you know, the fact that the different that again, for the inflowing observer requires this one entanglement, the outside observer requires this other, and they're not consistent. It's a simple argument, and of course, there's a real question: is this bizarre conclusion that there's a firewall true, or is there some subtle gap in the argument? And but there's another question which sort of has been exposed by this, which is the question of how well do we really understand quantum gravity? Because we thought we understood it pretty well, and now we thought we understood it in some sense perfectly, as I'll describe, and now there's this bizarre claim, and we can't decide whether it's right or wrong. So I'd like to so the real focus of this seminar is how well we understand quantum gravity, and I'll come back to sort of firewall-related ideas as I go along. But I'd like to back up a bit first. And so, you know, talks on string theory used to always start with pictures like this. So these are scattering amplitudes in string theory. And they're better than sort of just plain quantum gravity because each term is finite, whereas the loops in quantum gravity are divergent, and so string theory seems like it solves the high energy problem. But still, this is a series, it's a perturbation series, and it doesn't converge. So even if you know every single term, you don't really know what the theory is, and you know from other quantum systems that there are lots of interesting things that happen that you don't see in the individual terms, but only in the exact answer. And of course, there is an older version of this problem that is, for many years, quantum field theory we just understood as a sum of Feynman graphs. And again, the coupling is small, that's pretty good, but that series also doesn't converge, and so it doesn't define the theory, it misses important physics. And it was finally Ken Wilson who, by combining the path integral with the normalization group, explained in quantum field theory what the perturbation series was an approximation to. He gave sort of an exact construction of quantum field theory. And it's so exact that you can calculate it in different ways. You can just take the path integral, put it on a computer, and numerically evaluate it. And this is actually a practical thing to do. So for many years in string theory, this is all we had, and we kind of knew we needed the analog of Ken Wilson to tell us how to sum up the series. What is the exact thing? And it seemed that with matrix theory and with ADS-CFT duality, we had the answer. So the ADS-CFT duality is, well, let's say in a particular case, it's 2B string theory on ADS5 cross S5 is the same as n equals 4 super Yang-Mills. And this is again a quantum field theory. It's something we know, what it is, even non-perturbatively, again, thanks to Ken Wilson. And since we have this duality, it means that hidden in here is in particular the sum, the sum of all the string graphs. This theory remarkably knows how to answer this question. So let me say a little bit more about the actual dictionary between the two sides of this duality. So I'm going to always be thinking about the global anti-de Sitter space. So the field theory, the boundary where the field theory lives is a sphere, in this case a 3-sphere, and the gravity lives in the bulk. And first of all, there's a one-to-one mapping of states. And with the same energies as calculated in the Hamiltonians on the two sides. That's what you would always have in a duality. And then there's other observables. The most natural observable you want to ask about in the Yang-Mills theory is that you want to calculate, say, expectation values. The most common thing to talk about in field theory is things like expectation values of vacuum expectation values of products of local operators, gauge invariant local operators like that. And indeed, there's a dictionary for these. So calling things like this, just use curly O for the operators in the field theory, and then in the bulk there are fields, and I'm using X for the coordinates along the boundary and Z for the coordinate away from the boundary. So Z equals 0 is the boundary. So the bulk fields have this extra dimension. One has the ADS-CFT dictionary that says that basically these operators are the limit of these operators. The limit as you approach the boundary of these operators in the bulk, and you have to pull out some. You have to pull out the leading factor. This is to get a smooth limit is equal to these operators. And this is actually not so the dictionary between two sides goes back to Gubser, Klebanov, Polyakov, and Witten. This is not the way they stated it. Witten in particular stated it as he instead of talking about the operators, he talked about the generating functional for the operators. He talked about the path integral with insertions of one or the other. I like stating it this way because the path integral sort of is inherently time ordered, whereas this is an operator statement, so it's more general. In particular, one reason I emphasize this is, as Melanie was saying the other day, one gets the impression from a lot of literature on ADS-CFT that it's intrinsically Euclidean, and there's some trickery to getting Lorentzian answers, and I don't think that's true at all. I think this dictionary actually is neither Euclidean nor Lorentzian. That is, mapping of states is really a statement of the Hilbert space. It doesn't refer to what kind of time evolution you're doing. And again, the mapping of operators, again, it works equally well in Euclidean or Lorentzian space. If you try to translate this into a generating functional, then depending on what kinds of Green's functions you want, the generating functional is more subtle, but as a statement just of the identity of the operators in the states, this is equally good on both sides. Okay, and so again, these are the natural things to calculate. Just vacuum expectation values of products of local operators. And let's ask a question. So this is the quantity this is the quantity in the conformal field theory, and so by the duality, it's equal to the same thing. In the bulk. So what does this mean? So what this means is you have the bulk theory here, and now you're acting with field operators near the boundary, and so you're basically creating and destroying excitations near the boundary. And so you can think about the correlators in the dual field theory as measuring amplitudes where you throw things in from the boundary, let them interact, and then capture them at the boundary again. And actually, I should emphasize. I'm talking. There's ADS CFT and there's also matrix theory, and they're not identical, but they're very close cousins to each other. They both sum up this series. They're set up in somewhat different ways so that the questions that are natural to ask in the two theories are different, but in the end, they both let you answer the same question: what is the S matrix for scattering? But many other questions as well, but the one we usually like to ask: what is the S matrix for scattering in the gravitational theory? And so Melanie, was asking me, what can we calculate? And of course, for both matrix theory and for ADS CFT, there are many calculations you can do on both sides of duality and see that they agree. And Melanie and Katrin, of course, did some of the early ones with matrix theory, and in ADS CFT, many other such calculations have been done of various sorts, involving either 3-point amplitudes and long strings turn out to be a very simple setting. The calculations you can actually do are calculations which are usually protected by supersymmetry. The nice thing about the duality is that it allows you to know the answer to questions where you don't have a way to calculate them on both sides. So as I was thinking about Melanie's question and this discussion, what calculation would you do in the gauge theory to see this series? And one can, it's basically, again, you calculate some four-point function, and you go to some particular kinematic limit, and that's been described in the literature. But of course, on the field theory side, when you have a small curvature in the bulk, the field theory is strongly coupled, and so this series is answered in principle, but it's hidden in the strongly coupled field theory. You would have to solve the field theory numerically. There's probably things one can calculate that haven't been calculated yet, where you might be able to see. But a lot actually has been done with long strings that not with the sort of the short strings when you these guys, but with long strings which already matches the two sides in some detail. So we have so much, it's as with most dualities, we have so many things we can check between the two sides. We then assert that it must be true in general. So assuming this is true, again, as I said yesterday, I mean this duality is what I think convinced most of us that information is not lost, because you can in particular consider throwing in particles with enough energy that they actually form a black hole, which then evaporates. And so, and this is some perfectly, the gauge theory. Again, we know what gauge theories are thanks to Wilson. We know that they're unitary and obey ordinary quantum mechanics. There's no room, I think, for any mystery there. And so this is what tells us that even without being able to solve the theory, just because duality exists, it tells us that information is not lost. If you could go further, if you actually had the tools to solve the strongly coupled field theory, you would know not only that this S matrix exists, but you could actually calculate the S matrix. So hidden in n equals 4 super A Mills, whose Lagrangian I wrote down yesterday, is the actual detailed S matrix to throw in some collection of particles, form a black hole, and get out some other collection of particles. And again, it's hidden in the sense that one can reduce, one can say exactly what calculation one would have to do to get the answer. It's a calculation you could in principle do on a large enough computer. It's not a practical calculation, but it reduces even these very complicated quantum gravity questions to an algorithm. You know what the theory is. Okay, and so given this, it was tempting to believe that basically we had solved quantum gravity, that we had that this, interpreted correctly, is really the answer, a complete theory of quantum gravity. Well, it's a complete theory of quantum gravity with these special anti-de Sitter boundary conditions. And of course, the whole nature of the duality uses the existence of this boundary in a very definite way. And if you want to ask questions about quantum gravity and with other boundary conditions, say flat space-time or expanding space-time, obviously that was still an open question. But I think what the firewall discussion has really emphasized is that even here, within this nice box, our understanding of quantum gravity isn't as complete as we thought it was. So now, okay, I said we can consider some correlator. We can consider some correlator, which again corresponds to producing a black hole and letting it decay, and we know what calculation we have to do to get the S matrix. But suppose we want to know if this black hole that we formed has a firewall. And the firewall, again, need be visible. Everything I said yesterday, I perhaps didn't emphasize, didn't have time. Everything I said yesterday is consistent with the firewall being visible only to the inflowing observer. If you stay outside the black hole, it would look just like we've always thought. And so the question is if this theory of quantum gravity is as complete as we thought, what question would we ask in the field theory to tell us whether or not there's a firewall? And it seems like a question that should have an answer. So as I mentioned, if you think the simple things to ask about in the field theory are, again, vacuum expectation values of products of local operators. In quantum field theory, most of the information of the theory can be decoded from the spectrum, the scattering amplitudes, and so on, can be decoded from those correlators. But there really is a lot more information in the field theory than that, because again, these are local operators. There are also non-local operators like Wilson loops, although those, again, have a simple interpretation in terms of creating strings near the boundary. But there are, if I give you the, so here's the field theory lives on a 3-sphere. And if I give you the wave function for that field theory, there are many, many correlators between things in different places, which aren't simply correlators of local operators. And so the dictionary, the simple dictionary that we have is that the correlators of local operators measure what's happening near the boundary of the theory. But the idea has always been that if you looked at appropriate non-local observables in the field theory, you would be directly measuring things deeper in the interior of the space. And so in this way, in particular, it's been widely thought over the years that in this way you could make measurements even of the state of affairs behind the black hole horizon. Lots of people have written papers about this, including me, and the firewall has exposed the fact that those papers were optimistic. And seemingly, as a description of quantum gravity, ADS-CFT is not as complete as we thought. We have more work to do. So let me give you, I think, a little bit of background on how one would on this. It's called, well, it's these things are called precursors that measure things directly in the bulk. So actually, another way you might think about this is, suppose you have a Schrodinger cat experiment in the center of the space. So the cat is either alive or dead. One way to know whether the cat is alive or dead is simply to wait long enough and see. But this, again, this duality seems like it's supposed to be a complete mapping between the two sides of the theory. There's a one-to-one mapping of the states of the field theory to the states of the gravitational theory, and so without waiting, there should be some more elaborate measurement you can make on the wave function at this time that tells you whether the cat is alive or dead. So you have to figure out what is the operator that measures that. Or not, cats are messy, but what is the operator that we use to measure whether there's a particle in the center of the space? So again, there's some history to this idea. So let me sort of, to make the picture simple, let me blow up a region of the boundary here. So here's the boundary. And suppose I have some particle which is headed towards the boundary. And so when it gets to the boundary here, we can see it in the way I described. But now, how would if I have the field theory at some earlier time, what would I look at in the field theory to know that there's a particle here? And in fact, there's an answer to this which is kind of, it follows from the picture. So when the particle gets up to the boundary here, then again, there's some operator that tells me whether I have a particle near the boundary. So at this time, here's call this time t and this t prime. So there's some operator O of t prime that tells me that I have a particle at the boundary at that time. But of course, we can time evolve. So there is some, I'll call it p for precursor, which is just this same operator, but evolved back in time. And this is a very messy thing. Again, it's not something that you can calculate in principle because you're doing time evolution in a strongly coupled gauge theory. But of course, what this is this is just this operator. So it's just the same operator. It's simply asking the question at a different time. And so if we measure this operator at this time, we would get the same answer we would get from measuring this operator at this time, and so we would know that there's a particle which is headed towards the boundary. And that's why they're called precursors, because they let you know that something is going to be there before it gets there. And they're messy, but I can say a little bit about them. So again, these operators, this is again something like a local operator, which means that it creates some number of fields at a point. And if we evolve this operator forward in time or backwards in time, either way, those fields will spread out in different directions. And also they'll interact with each other and so on. And so what this operator does is, it's still gauge invariant, that's important, but it's a very non-local operator. It involves the fields spread out on some sphere, and maybe in the interior of the sphere in a very non-linear and non-local way. So that's what this operator is. And so this operator, and there's a recipe for it, but by measuring this operator at this time, we know whether there's a particle in the interior of the space. And I'm focusing on operator, but you can also think about this from the point of view of states. If I act with a local operator, I create a particle near the boundary, and then it moves inward. In the field theory, what's happening is what I just described. The things that I created spread out. And so there's some sense in which things that are small, this is kind of the holographic dictionary. Things that are small in the field theory are close to the boundary, and things that are big in the field theory are deeper into the space.
So how is it determined the form of U?
So U is just the time evolution operator in the field theory, e to the minus I H E minus
What do you
E
think
prime.
H then?
Hmm?
So what is H?
H is the Hamiltonian for the CFT.
Oh,
Okay. So you know, you can.
so this is just quantum mechanics.
It's just quantum field theory, but it's just quantum mechanics. It's just quantum mechanics. And this expression is meaningful. It's you know, I don't know of any case where it's actually been useful for calculation because again, this is a strongly coupled field theory. But it tells you what the form of the answer has to be. That there is an answer, and that it's messy, but it's messy in this particular way. That it's spread out, and the deeper the particle is, the more it's spread out. So again, there's a long literature on these precursors going back to even the year after Maldaceni's paper, and continuing up till this past year, people refining this, especially looking at sort of 1/n corrections and the names that are most associated with this are Kabat, Lifshitz, and Low, but there are many others. Okay, so this is an old story about going. So there's the classic GKPW dictionary, which is the sort of basic statement of ADS-CFT that we all begin with, and now here's a way to build on that to ask a larger set of questions about what's happening directly in the bulk. And again, this always seems to me like a good direction, but now I want to take it one step further and suppose that there is a black hole in the bulk, and there's some excitations or cats or whatever behind the horizon. And I want to use the same kind of idea to ask whether one can make a measurement in the CFT to know about the state of the things behind the horizon. And again, many people, including me, have written papers saying the answer was yes. And now I think the answer is no. So let me draw the black hole geometry. I guess it'll eventually evaporate, so it looks like that. But so this is a black hole in ADS. So there's the boundary, and we've thrown in at some early time some shell of matter to make a black hole. Before that, there was just empty ADS, and then there's a horizon that forms. Okay, and actually, so now I can talk. I remember yesterday I had my operators B, B prime, and A. So let me again talk about B. Let me talk about the Hawking mode outside. Again, for Hawking mode outside, we can follow it to the boundary, and so we can at the boundary use the GKPW dictionary to figure out what is the corresponding operator in the CFT, and then we can evolve it back, and so we can have something, I'll call it P sub B, and so P sub B is some operator in the control field theory, which is equivalent to the corresponding operator, raising or lowering operator here, and so there's the dictionary I described just works the same way. Now actually, I want to talk about now doing the same thing behind the horizon. Before we do that, I want to return to the firewall, and so I gave you yesterday one argument for the firewall, which is the original one, which again starts with these assumptions about no drama and unitarity, and concludes that we get an impossible quantum state. What I'd like to do here, since I like ADS-CFT so much, is to try to use ADS-CFT sort of more directly to address the question of whether there's a firewall. And the argument I'll give you is a very simple one. It's actually largely due to Raphael Fuso. And let's consider, so B is the lowering operator. So let's consider B dagger B, whose image in the conformal field theory is P sub B dagger P sub B. So again, these are the same operator just as represented in two dual descriptions of the theory. And this is a Hermitian operator can diagonal. It's basically a number operator. So let's take a basis in which this is diagonal. You can always do this. Now, there's some other modes. So there's the mode I called A, which is the smooth mode across the horizon. And there's the mode B prime, which is the part of A which is behind the horizon. But now, the question is, are we in the infalling vacuum? Are we in the state which is annihilated by A? And now, as I described yesterday, the A, because of the relative redshifting between the infalling observer and the observer at infinity, the lowering operator for the infalling observer is not the same as the lowering operator for the asymptotic observer. And so if A psi equals 0, then n sub B has a thermal, let's call this n sub B. N sub B has a thermal distribution. Okay, this is again just Hawking's result. If the infalling observer sees vacuum, then the asymptotic observer sees a thermal distribution. But now I have a basis here. I have a basis here in which n sub B is diagonal. It doesn't have in every basis state. In every basis state, this mode has some definite number, 0, 1, 2, or 3. It doesn't have a thermal distribution. So none of these basis states are the infalling vacuum. They all have, again, definite numbers of B oscillators, and the vacuum here is some very precise superposition of 0, 0, and 1, 1, and none of these are that. So we have a complete base, and this, I'm focusing on one particular mode of the field here, but this statement holds for every mode, I can consider every mode of the field. And the conclusion is that in this number operator basis, every mode of the field is excited with probability of order 1. So in this basis, every state has a firewall.
Wait, why? Why do you say every state has a firewall?
Because in this basis, in every state of this basis, the A modes, the modes the infalling observer sees, are excited with probability of order 1. Okay, if they weren't excited, then n sub B would have a thermal distribution. If n sub B does not have a thermal distribution, they're excited with significant probability. So in every state of this basis, the A modes are excited with probability of order 1, and that's the definition of a firewall, that the modes seen by the infalling observer are excited. So this sounds different from the argument I made. Okay, actually, this of course is a basis of states, but if it's true for a complete basis of states, then there might be special states, and there probably are special states where the firewall cancels by destructive interference. But if it's true in a basis of states, then it's true for typical states. Now, if you think, I want to compare this argument with one I made yesterday because it's very different in flavor. Yesterday it was focused on this entanglement. Actually, these states are not entangled at all. These are actually pure states. these are actually pure states in which the number operator has a definite value. So this is actually providing you with a set of pure states that have firewalls. So it seems like a very different argument. It still uses the same basic assumptions. It assumes quantum mechanics in the sense that we're assuming that there's a nice field theory dual. It assumes that nothing funny happens outside the black hole as we propagate from here to here. And just with those two assumptions, that nothing funny happens outside and that we have a field theory dual, we conclude that the inflowing observer is going to see everything excited.
Is there a way to make the relation between the bases more precise?
So, it's a good question. You could certainly do this. That is, you could. In fact, yes. Yesterday I wrote that B, the outgoing mode, is some linear combination of the raising and lowering up. So the lowering mode here is some linear combination of the raising and lowering modes here.
Wait, what is A prime?
Oh, sorry, A dagger. A prime is A. So B and C are just numbers that I'm not calculating. But now we can invert this. If we invert this to express A, we have to express A. We have to express A in terms of both sets of modes. So the inverse relation is that A, I'll just make it what A is equal to some. I need a bunch of letters. D times B plus E times B dagger plus F times B prime plus G times B prime dagger. So the lowering mode near the horizon is some sum of raising and lowering modes for both this half and this half of the other basis. And now you can take the number operator, n sub A, which is A dagger A, and you can fill this in and write this out. And then, I won't go through the details, but you can write this as a sum of squares, and if B is in an eigen, if the number operator for B is an eigen, if you're in an eigenbasis for B, you can see that this is greater than or equal to some number of order 1. So that would be right. So that's a more precise way to say what I just
So
said.
when I need to sum the direct numbers, TE and the
Yeah. So yeah. So these numbers are all
From
things.
there it works.
These numbers are all things like e to the minus beta omega over 1 minus. You know, these are all numbers from the Hawking calculation, the Bogoliubov transform coefficients. So the numbers, these are all numbers that have this form. In fact, to be more precise, you probably want to include indices because these are all complete sets. And so these are actually matrices, not numbers, but the matrix elements are all of this form.
But when we need to use this form, or are you saying that, let's say for generic?
Generically, these are numbers of order 1. This argument is very robust. It doesn't depend on details. So these are just all non-zero numbers of order 1. And therefore, this number is order 1 if n sub b is diagonal. And that's a calculation that we can do later. Yeah.
How to say firewall is behind the horizon instead of slightly outside?
Good. So good. So there is nothing in this argument that restricts. So basically, to measure the, well, it could be. This is an argument by contradiction. But what the contradiction says is that if we measure the mode A, we're going to get a non-zero excitation number. How do you measure? To measure that, you actually have to do a measurement that extends in the entire space. if you know, to measure this mode, so the question, there's this question, where is the firewall? And the statement, so this is a mode that has some wavelength, it has some size. And to measure the number operator for that mode, you have to do a measurement that really spans this entire distance. So the size of the firewall is just depends, is the sort of inverse size of whatever is the highest energy mode that you trust field theory for. It's something up at the cutoff. And it's interesting because this discussion allows for the possibility that there might be something visible on the outside, but to be sure that, but it only definitely implies that there is some deviation from the adiabatic principle if you do a measurement that extends all the way across the horizon. Now, there's this old notion of a stretched horizon. So the stretched horizon was, the stretched horizon was another piece of intuition that goes with black hole complementarity. It was the idea that the observer outside, what the observer outside sees is that something falls into the black hole at about a Planck length from the horizon in some frame. It's absorbed by a membrane. It rattles around and thermalizes and then is re-emitted later. And so, you know, when I think of the firebrain, I think of the firewall as being what we used to call the stretched horizon. Now the stretched horizon had this other supposed property that although this is what the outside observer sees, what the observer falls through doesn't perceive it. They pass through into the interior. And if the firewall argument is right, I think what it's saying basically is that the stretched horizon picture is still what you see from the outside. That doesn't change, but the other property that it was supposed to have, that you can fall through it, isn't consistent. But now, okay, there's a funny thing about this argument, though. Which is that if you think about the structure of this argument and the structure of all firewall arguments, we use the conformal field theory. We use the fact that B had an image in the conformal field theory and talked about its state in the conformal field theory, and then we use some indirect argument to conclude something about the mode A. So there's a natural question to ask, which is the question that I thought should have an answer, which is, what is the image? Why don't we just directly think about how we would calculate, rather than this indirect argument, how would we directly calculate the excitation number for the A mode, or for that matter, for the B prime mode, for something which is entirely or partly behind the horizon? And the interesting thing is the precursor dictionary that I described to you no longer works because the dictionary goes wait for it to come out to the boundary, see what the operator is, and evolve it back in time. But of course, the modes behind the horizon don't ever come out. They hit the singularity. Actually, the precursor dictionary is interesting because you can run it in either direction. We could also evolve the mode back in time and then forward and construct it that way. Now it's kind of odd that we have sort of two different prescriptions. It's because we're sort of integrating sideways in space, which is not normal Cauchy evolution, but these are consistent. They have to be consistent but because of the duality. And we could try to do the same thing. We could take this mode, follow it back in time, and then out to the boundary. And that's what, again, a number of papers said. That you could construct these modes behind the horizon by this process. But on closer examination, there's a problem, which is that when you follow things back in time near the horizon, because in this conformal diagram, you don't see it. You don't see distances, you just see causality. In the coordinates that I used yesterday, Finkelstein coordinates, you see more directly that as things are moving back in time, and they're actually getting closer to the horizon, they are being squeezed and blue shifted to higher energy. And so when you try to follow this back in time and construct these interior operators, if past a certain time, the blue shifting is so great that you can't really trust your understanding of the theory here, because this is the infalling star or whatever that formed the black hole. And the energy of this mode in this rest frame will very quickly exceed the speed of light. The exact time, see, that's right, will exceed the Planck energy, The exact time at which that happens is actually this scrambling time. It's T scrambling, which is the black hole radius times the log of the black hole radius in Planck units. And if you just do the geometry here with this blue shifting is exponential, that's where the log comes from, and so this collision becomes trans-Planckian. And so we don't know how to follow the evolution back further and construct these operators, and in fact, probably once this happens, you get a singularity and there is no earlier evolution. So this is one of a number of arguments that suggest that although this operator has a perfectly good image in the conformal field theory, well, this operator the very best situation is that it might exist in the conformal field theory, but we don't know how to calculate its image because we have to solve this incredibly messy problem in the book. But most likely this operator doesn't exist at all. And so there's a sharp limitation to what we thought was a complete theory of quantum gravity, and again, and a sharp distinction between what look from the point of view of a local observer, these are very similar things. They're the same kind of mode, just slightly displaced. But the one just outside the horizon has an image in the conformal field theory. The one behind the horizon does not. Of course, if there is nothing behind the horizon, if there's some extreme firewall that just erases all of that, maybe there's no problem. But you'd still need a theory. You'd still need the conformal field theory to tell you how and when this firewall forms. And even if you could solve the conformal field theory completely, even if someone gave you all the wave function, everything you want to know about it, we have no idea what is the observable that would tell us whether there's an interior or not. So the lesson I take from this is that we gave up too soon on looking for sort of the non-perturbative construction of quantum gravity, that there is something more, whether it's simply a more complete version of ADS-CFT that sort of has another coordinate patch. Well, I think it's more likely that what we really need is we've been kind of using the CFT as a definition of the string theory, and of course it's not that trivial because we have a lot of information about the string side, and the duality has to be consistent with all of it. But we've been using this duality, we've been using this side to give the definition of this side, string theory and gravity. And I wonder if we gave up too soon on looking for an actual non-perturbative construction of string theory directly. You know, we used to talk about string field theory. That doesn't seem like a promising direction. I'm not sure what is a promising direction. The only people I know who are really trying to do this are Tom Banks and Willy Fischler in what they call holographic space-time. And I have to say, it's a hard problem, and I don't understand their work, and I'm not sure. You know, some of their intuitions are probably correct, but you know, the whole discussion of the firewall has left me feeling as though we have to go back to this more basic question of understanding quantum gravity.
And why are we talking about non-perturbative physics? Couldn't you pose the same question just in GR?
Well, you could pose it, but we know that there are things that happen, monopoles, instantons, brains, that perturbation theory doesn't know about. And so even if you, so the perturbation theory, we know that the perturbation theory doesn't show a problem here. But we know in other cases where the perturbation theory doesn't show a problem, but then something non-perturbative happens and changes the story. So I really think this is, I think this is a non-perturbative question. So, not surprisingly, I've taken longer than I thought. I want to take say my last 5 minutes to just mention, building on this, this ER equals EPR idea. It's kind of the most interesting thing that's come out in it's kind of the most interesting thing that's come out in response to the firewall, and maybe where things are going. So this is, if you take de Sitter space and you take the black hole solution, and instead of forming it in collapse the way I described, you take the maximally extended vacuum solution that looks like this. It has two sides, the side I've been talking about, and another side. It has two boundaries, and then it has this interior region. And so, because there are two boundaries, it's natural to think in terms of two copies of the control field theory, one with operator O right and one with operator O left. And the claim is that in fact, this extended geometry, this claim goes back to Maldacena about 12 years ago, that if we take, and I'll tell you what the state psi is in a second, if we take some expectation value now in two copies of the control field theory of some product of local operators on both sides, then again, this is equal to the path integral, the expectation value in the bulk, with, again, the corresponding, as I said before, the limit as z goes to 0 of z to the minus delta of x, z to the minus delta of y, phi. So the dictionary, so the same dictionary as before still holds, but it holds in two copies of the field theory. And what it says is this maximally extended geometry calculates the correlators between the two sides. And I have to tell you, actually, to make this meaningful, I've got to tell you two things more. I'm going to tell you what this state psi is. It's a particular entangled state of the two control field theories. It's called the Thermo field state. So it's the sum over all the energy eigenstates. And it has a thermal factor. And then it has its diagonal. So this is the left side. It's so it's diagonal in the energies on the two sides, and it has some thermal factor. And on the right side here, I have to sort of to tell you how to do these bulk calculations. I have to give you a boundary condition in singularity, and the boundary condition is that this is calculated in the Hartle-Hawking state, so that you define the various propagators by using a Euclidean continuation. And this, I like this because, again, it's a sharp statement. And although it seems like it brings in some very new ingredients, namely the idea of having two copies of the conformal field theory, it actually is derivable from things we already think we understood. Because if I consider this spatial slice through here, what's called the Einstein-Rosen bridge connecting the two sides, that spatial slice, doesn't know, since it's a t equals 0, it doesn't know if we have this Lorentzian picture or the corresponding Euclidean picture. So that spatial slice is the same as a spatial slice through the Euclidean black hole geometry. And this is something which, this now just has a single boundary, and it's something for which we know the dictionary. But if you take this sort of known dictionary from the Euclidean case, and you now rotate from Euclidean time to Lorentzian time, you derive, as Maldacena showed, this result, which now seems like it goes much further because it tells you about this funny system which you have two copies of the control field theory. Okay. Now this is very interesting because if we think about the modes behind the horizon, in this case, well, they depend on what's happening on the other side, what we threw in from the other side. So it's not clear how this relates directly to the firewall discussion. Well, it's not clear how it relates to the previous discussion in my talk because it's saying that these modes are sort of represented in this case, but they're represented not by operators in the side we thought we were looking at. They are represented by operators in this other field theory that we didn't know about, or that wasn't there for the black hole that formed from collapse. But anyway, starting from this, more recently, Maldacena and Susskind. So actually, this, by the way, seems like this black hole does not seem to have a firewall. I say that because, again, it seems as though the correlators between this side and this side are correctly given by, again, calculating the correlators in the field theory. It seems by the argument that I just gave that these correlators are correctly given by calculations in the smooth extended geometry. But again, we know the firewall argument only says that typical states have firewalls. It certainly is expected that states that are prepared in a special way could be free of firewalls, and this particular state seems to be free of firewalls. Now, this is a state in which the two sides are very strongly entangled, because in fact, if you look at this, the point of the thermal field state is, if I trace over the left-handed state, the density matrix of the right-handed state is perfectly thermal. So you can think of this as being a system and a bath that are perfect in either order, that are perfectly entangled. So there's a strong entanglement between the right and the left here. So Susskind and Maldacena say, hey, let's take the black hole we were talking about yesterday, which forms and starts to evaporate. And when it's half evaporated, we're going to collect those photons, and we're going to use them to build another black hole. And we're going to do it, we're going to feed this through a quantum computer in such a way that for these two black holes, we exactly produce this state. Now what I said here, so actually there's a slogan, so what I said here, actually, that's before I come back to this new thought experiment. What I said here can be summarized by the slogan, ER implies EPR. Now, ER refers to the fact that you have an Einstein-Rosen bridge. You have this spatial slice with two asymptotic regions. EPR is just shorthand for entanglement. So this is saying that if you have an Einstein-Rosen bridge, you have two highly entangled systems on the outside. Now, what Susskind and Maldacena have suggested is, suppose we take the black hole that we formed by collapse. We collect the photons, we properly process them, and now we produce a second black hole in such a way that the two black hole state is this. So then they want to claim that in fact in this case, well, it seems reasonable that the geometric realization they get over here is the two-sided black hole. So they want to claim that you can take what you thought was a black hole that you formed in collapse, and by letting it entangle with another system and then processing that, they're claiming that you can actually form the interior of this black hole, and moreover, by further, sending messages into this black hole, you can send a message to someone who jumps into this black hole. So now this is the other direction. This is saying if you have entanglement, then automatically there's a related geometric connection. Now, it's not clear whether this construction, if it's true, implies that there is a firewall or is not a firewall. One of the things that Don Maroff and I is simply said, suppose we take, instead of this, very specific entangled state on the two sides, suppose we take a state that's just as entangled, but not in such a special way. And you can sort of take a typical entangled state. And now, in this state, there are strong correlations between the two sides, which is consistent with the idea that there's a geometric connection. If you take the typical entangled state of the two sides, you can show that, in fact, the correlations between the two sides are exponentially small in the entropy of the black hole. So what it suggests is that this particular state may not have a firewall, but our interpretation was the generic one does. Another possible interpretation, which Juan suggested, is that the generic state still has a geometric connection between the two sides, but it's a much longer throat. So by throwing matter into the throat, you can make it longer and longer. And so another possibility is that the geometric connection is still there, but that it's not so simple.
Can you repeat the argument? So why would I learn from the presence of a second black hole about the interior of the first black hole?
Isn't that strange? Isn't that strange? If anybody but Juan said it, you would just. So good. So we know that if we start with the interior geometry, that there is a dual description, at least of the correlators outside the black hole, in terms of a specific entangled state of two conformal field theories, of two black holes. Now they want to say, suppose we produce such a state by the process that I described, starting with one black hole and then making a second one in a very precise way. Then if this is an identity, if this geometry and this conformal field theory state are in one-to-one correspondence, then they seemingly have produced the connection by that manipulation. The other possibility, which I think also to be taken seriously, is that it's not one-to-one, that there is more. It may very well be that quantum gravity, and it kind of is consistent with the earlier part of my talk, that quantum gravity has more data than is reflected in the boundary theories. And so simply knowing this doesn't tell you this. Now, I'm not sure, I have to say, it's kind of nice in subjects like duality to believe that things are one-to-one. They usually work out that way. And so this is an attractive idea. But if this is true, so starting from something which, again, is I think, very well established. This part of the dictionary seems like it's just an analytic continuation of things we already understood. Starting from this part of the dictionary, if we assume that this relation is an identity, then we really get to a modification of quantum mechanics. Because what this implies is that my picture's gotten kind of messy, so what I'll do is I'll erase everything but the black hole we started. We form a black hole. We let it evaporate. We collect half the Hawking radiation and send them off to somewhere else or somewhere where someone does something to them. And then we later jump into the black hole. The statement is what we see depends on what was done in this black box over here. That's what Juan and Lenny are saying. So it really is using EPR, using entanglement to send information. It's something that you cannot do in normal quantum mechanics. Now, we all thought that the moral of ADS-CFT was that quantum mechanics is not modified. And certainly, what ADS-CFT tells us is that if we're the observer outside the black hole, or if we're the observer at the boundary of space-time, we see ordinary quantum mechanics. But the observer at the boundary of ADS is very special because ADS basically the metric is not fluctuating there. The fluctuations go to zero. You're a very special observer. and observers in the bulk, and in particular observers behind the black hole, might be qualitatively different. And so this is one of a number of ideas, but this is the one which is, I don't know whether this tells you there's a firewall or not, but this is, you know, one of the attempt. Well, it's one of the attempts to avoid the firewall, and independent of the firewall, you know, this is a natural train of thought. But it's a train of thought which really implies that whatever is the big framework for quantum gravity, quantum mechanics is not quite what we think it is, because we can use EPR correlations to send information, again, provided that the receiver is safely behind the horizon of a black hole. A very strange thing. So I think this is an interesting idea. It might simply be inconsistent. It might be that if you think about more thought experiments, think about, it's not even clear that there's a consistent set of rules that they've given for what the interior is given various operations on the outside. But again, the moral of my talk is we don't understand quantum gravity as well as we thought we did, and there's more work to do. So, thank you.
So going back to our G flow,
Yes.
which was asking about yesterday.
Yes,
so
yes.
imagine, I understand we don't know how to deal with our G flow in, say, coordinates that cover the entire solution. But you could imagine mapping the static patch, which we do understand. Trying to sort of go a little bit away from the static patch, and mapping that to the original coordinate.
But instead of, you mean to set a patch of Pacific?
Yeah, well, sorry.
Or for the exterior. Or there can be just this
What
patch.
is it called? The Poincaré.
This patch.
coordinate.
Okay.
Yeah.
Right. So the renormalization group seems to want to, construct the usual sort of Schwarzschild time and radial slicing. An object of some size in the Kamal field theory seems to correspond to an object of some corresponding depth in this coordinate system. In fact, that's another one. And so, once you're behind the horizon, it's not clear what the analytic continuation of that. I mean, how do you?
So not even in a sort of an epsilon away from the horizon.
It's kind of a matter of causality, right? I mean, causality is, it's in, in quantum gravity is causality. How precise is causality in quantum gravity, right? Can things fluctuate outside the light cone in some useful way?
But okay, then I could rephrase the question and say there was some work by, I think, Giddings and I'm sure other people a long time ago on understanding correlation functions, prescriptions in global coordinates.
Yes.
I don't know.
Yes.
So that was, again, not the standard KITP dictionary, right? It's slightly different lessons.
Right. So you want to, right. So, I mean, I think if you're asking the question you're asking, it's one which is right. So the field theory on Minkowski space constructs the Poincaré patch. And there is the whole rest of global anti-de Sitter space. Right. And so the question is, so this might be a model for what we need to do to find the interior. So, if you follow something across the horizon, you're now on the field theory in flat space. And again, as it approaches the horizon, it's going to infinity in the field theory. The field theory for the global space is a three-sphere. It sort of is like Minkowski space with sort of an extra point at infinity. And so somehow, by adding just one point to the field theory, you get a much larger space. Now, I think you're adding, although it looks like a point, I think there's really a lot of data there, because you're kind of saying what the boundary conditions do. But I've often puzzled over this, the fact that indeed, that there's this, I mean, is there some analog of this extension for the black hole? And I don't know the answer to that. I mean, in some sense, having a second copy of the CFT is a little bit like that. It's doubling, you get more space by doubling the field theory. So maybe there's a principle there.
Any other questions?
You say that ER equal to EPR implies modification of quantum mechanics.
Yes.
But that modification implies violation.
No,
of
no,
authority.
I think you said it backwards. I'm saying, well, sorry, equals implies modification. Sorry, what, sorry?
Then implies violation of causality.
It avoids violating causality because it's a one-way, messages are one way. They only go this way from here to here.
Instantly. Or
Instantly.
take
Yes,
some
yes,
time.
but instantly, but you can't make, in order to violate causality, you've got to make a loop. You know, you send a message this way, you send a message there, and then there. But because this is a one-way EPR experiment, you can't close the loop to violate causality. It's very tricky. I mean,
So if there is one person can say two sides of the black holes.
it's the interior. though.
He would feel the violation of causality,
But the fact that you're behind a horizon, I mean, it's the fact that you're behind a horizon that protects the world, that protects causality. It's a crafty idea. I think it's worth developing. I try to make, it needs rules.
So that's,
I don't know about that anymore.
any other questions?
Yeah, just two very simple questions. Don't you think when you were doing this experiment with collapsing black hole collective focus,
Yes.
don't you think, this assumption of some kind of quantum computer, whatever, don't you think it would affect this measurement that you will never, ever create the same black hole? Or if you do, it will be completely different, or it will take exponential long time? That's number one question. Number two is just, I don't want to embarrass you, but what kind of experiment can I devise in order to test any of your statements?
Okay, good.
Because look, just in order to explain you less embarrassing, because we know about quantum mechanics,
Yeah, yeah.
right? We know about EPR paradox, which just can be resolved with density matrix analysis, and has been verified in quantum optics experiments.
Wait, say this, I'm sorry, I missed that.
So EPR.
Yeah.
So you see, you were talking about something that has solid ground, another thing, just all of this talk.
Yeah. So, let me take your easier question first, which was, sorry, the first one was, I wanted to answer.
About this paradox.
Oh, yeah, can you actually, right. So, well, actually, the answers to both parts of your question go back to Hawking. So, Hawking's paradox, if you actually want, I mean, although people didn't talk about quantum computers when he wrote his paper, it implicitly requires, it implicitly requires a quantum computer the ability to manipulate a quantum state arbitrarily precisely, because to decide whether your final state is pure or mixed, you have to do some very fine measurements in many bases to figure out which is which. You have to sort of capture all the outgoing particles, or at least half of them.
Sure, but
And
that
then process them.
you're aware about the current state of quantum computers, they can add two numbers.
They can now, yeah. So as a question of what you can do in principle in quantum mechanics, there doesn't seem to be, and people have objected to some of the discussion is perhaps there doesn't seem to be an objection in principle to the idea that you could carry out this experiment. It's out of reach of anything we can reasonably measure now, but it doesn't seem to be something you couldn't do in principle. Now, as to experimental verification, I want to come back and imagine that you asked Stephen Hawking that same question in the past, because people spent a lot of energy on the original information paradox, which I described yesterday, and certainly there were times when one would think, this is so abstract, is it really important? But in fact, that paradox led to ADS-CFT. It led us to understanding this unexpected connection sign between these two things. And that does have, well, it makes mathematical predictions about the behaviors of quantum field theories, which can be verified, have been verified. And it also lets us unfortunately, it doesn't let us sharply match the real world, but it lets us understand features of the quark gluon plasma and other exotic phases. But I mean, you know, for me, you know, Maxwell didn't know that he was going to discover what light was. And for me, the puzzle is still that we don't have a consistent theory that unifies gravity and quantum mechanics. And this seems like the most fruitful way to get there from here. So I don't have to answer your question, but I expect to have I expect at some point in the future there will be an unexpected answer to your question.
The answer would be no, right?
No, that would be expected. Yeah.
Okay, so why don't we continue upstairs?